Am I audible?
Yes, sir.
Yes, sir.
Am I audible?
Yes, sir.
Yes, sir, you're audible.
Professor Chari,
Very good morning. That's great.
very good morning. Very good morning.
Just in 2 minutes, I'm there with you.
Yeah.
Are you able to hear me, please? All of you?
Yes, sir.
Shall we start, or are we waiting for anyone? Dharmendra,
We can start, sir.
shall I start? Sorry?
He said yes, sir.
Okay, thank you. So, very good morning to all of you. As you all know, today we are celebrating the National Science Day. The National Science Day is for those who believe in science. The National Science Day is celebrated in honor of the discovery of the Raman effect by Indian physicist Sir C.V. Raman way back on February 28th, 1928. It's a discovery that led to the award of Nobel Prize to Sir C.V. Raman in physics in 1930. It is marked to raise awareness among the people about the importance of the science to the society. Since 1987, it has been celebrated every year. During the last 2 years, our entire population have had silent lessons of science and developed zeal in science. Today, I am brave to say that we all have cultivated a scientific temper that is encrypted in our constitution. On this occasion, today, I have great pleasure in introducing the today's speaker, Professor Avijit Gangopadhyay. He's a professor at School of Marine Science and Technology at the University of Massachusetts, Dartmouth, where he teaches ocean circulation and modeling, ocean atmosphere dynamics, and introduction to climate. He previously served as the interim dean and associate dean of SMAST. He is known internationally as he has held multiple visiting distinguished and honorary professorships at Harvard, the Institute of Oceanography of the University of Sao Paulo, the Indian Institute of Science, Bangalore, and Institute of Technology at Kharagpur, and more recently at IIT Bhubaneswar too. This is where, during a meeting just few weeks back, I happened to bounce him and I requested him to visit us and give a talk. And I felt that this is the most ideal day to listen to him, primarily because we are now intending to open up a new department, a Department of Earth and Environmental Sciences. I should also share with that he has been involved in the inception of multiple academic programs, starting from establishing an international dual degree PhD program and UMass USP, to the rise of the ocean research centers at IIT Kharagpur and IIT Bhubaneswar, as he was one of the founders of the Center of Oceans, Rivers, and Land Sciences at IIT Kharagpur. His research interests and contributions include the dynamics of western boundary currents, operational ocean modeling, and data assimilation, basin scale climate related processes, and multi-scale, multidisciplinary data model synthesis studies. Professor Gangapachay holds a BTech in Naval Architecture from IIT Kharagpur and MTech in Applied Mechanics from IIT Delhi. He earned his PhD in Ocean Engineering from the University of Rhode Island, where he first studied the Gulf Stream. He was a research associate at Harvard University and a scientist at the Jet Propulsion Laboratory before joining UMass Dartmouth. He is a Fulbright scholar and has long-standing collaborations with MIT and the Woods Hole Oceanographic Institution. He has numerous publications in many international journals and books during his long career. I have already shared with you all this information and also about the information about his newly released textbook, which provides basics for the study of oceanography, covering ocean properties and circulations and their modeling, with applications to both interdisciplinary and climate problems. Without taking much time, I take the pleasure on behalf of entire fraternity of IISER Berhampur to invite Professor Avijit Gangapachay to deliver this public lecture on this auspicious occasion of this year's Science Day. Professor Avijit Gangapachay, please.
Professor Chari, it's been a privilege and honor to be here with you all. And good morning to everyone from a snowy night in Massachusetts. So I think you have said it all, and I don't know how to even thank you for inviting me to do this. And it's a real honor, and I hope to entertain you for next, if you indulge me, for 45 minutes. And I will take you through some of the work that I know are important to my heart, and I think you will like the ideas that is contained in those 45 minutes. And me and Professor Chari have talked about it. So thank you very much for giving me this opportunity to speak to you all. And with that, I would love to visit your campus sometime.
Please.
I would like to. I was there in January, right? 5th of January. That's when we met. And I would love to come to the campus and see you all in person.
Please.
I would say that allow me for 2 minutes to share the screen, and then we will get going with the talk. Feel free to stop me if you want to ask a question. Do not shy away from it, and do not keep it for the last moment. You might want to keep it for the last moment. And I do not know if someone is keeping the chat box.
Yeah.
Maybe Dharmendra or someone, Professor
Okay.
Chari can designate to do that, and that will be helpful to me. Then I don't have to do it, and I can just answer the chat questions. Is that okay?
Yeah, please.
Okay. So, Mr. Dharmendra, please help me.
Yeah. Yes, sir. You can
So
say.
I'll share the screen. How is this?
Good.
Seeing it? We should move it to slideshow, I think.
Yes.
Okay. How is that?
Very good. Very clear.
You can choose your pointers.
Wonderful.
Okay.
Please.
So let's begin, and thank you again. So what I'm going to do is I'm going to talk about the future of our Earth and where we are and where we want to go from where we are. So, and my acknowledgements to all the funding agencies as well as Fulbright and IIT Kharagpur and IIT Bhubaneswar, where I've been visiting several times, and you will see it in my talk on when I give the talk. Okay, so as this is a science day topic, so essentially our great respect for Bharat Ratna Sir C.V. Raman. And then I will dive right into our home, the Earth, the climate where it is going, a little bit of history. I love history, and I would like to share some of the important things. And then we will talk about some opportunities that exist ahead, and then the final message of today. Okay. So when I look to, I mean, C.V. Raman was a physicist, and in his own right, he did the work on the Raman effect and spectral analysis and spectroscopy and all that. But this is what he said in one of his um, lectures. In the history of science, we often find that the study of some natural phenomena has been the starting point in the development of a new branch of knowledge. And I think that is very important saying, the coming from him. He's generalizing how science happens, how new knowledge is gathered when you start looking at natural phenomena. And this is where climate is. When we started looking at climate, we did not know where we will be 50 years back. But this is where we are. I mean, everyone, climate change has become a common man's word of mouth. I mean, everybody knows that the world is warming. And so, what do we do about it? And so, let me take you through some of the important things. Um, can you guys hear me?
Yeah.
Yes.
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 Very nice
Yes.
to hear.
I wanted to move this little thing that was obstructing my view.
Please.
Okay, sorry. Okay, so our home or the earth is actually, if you think the Western hemisphere and the Eastern hemisphere are in front of you, and if you think, it's actually nothing but a ball that can be put on a palm of someone, if you will, and then that ball will have a radius of about 6,400 kilometers, which we know, and this is what you imagine a ball, right? And it has 6,400 kilometers of solid earth. Then on top of which there is a thin layer, 3/4 of the surface of the earth is actually ocean. And so that's the hydrosphere, which is about 4 kilometers thin or thick. So 6,400 kilometers of solid earth with a density of about 1,000 to a ocean with a density of 1, and then an air or atmosphere with 10-kilometer active thickness, right? 30,000 feet, 10 kilometers. So these three, solid earth, the hydrosphere, or the oceans with 4-kilometer thin ribbon around it, then 10 kilometers of air around it, whose density is 1,000 of the ocean. These three together makes what we know as the physical system of the climate, right? The ocean, the atmosphere, and the solid earth. Then you have the biosphere, which is us, the human beings and animals, and from the biota to the ocean, fish and the whales and all that is our biosphere that we habitate in this climate of ours. This thing gets its energy from the sun and then goes around the sun 365 days a year and rotates on its own axis 24 hours a day, right? Once in 24 hours. That's the system that we talk about when we have to understand that system, and then it's a nonlinear Navier-Stokes equation based rotating Earth system that we have to understand, and then we can predict what's going to happen in the future. The physical system is one thing, the biological system is another thing, but they're all connected in one thing that we call this climate system. It's a complicated thing, but I will tease it out to some elementary things that will make more sense to why we want to attack this. So, talking about climate change, there are two metrics. One of them is very easy. It's temperature. It's the warming. We feel it. The Earth's temperature is equilibrated to a certain 18 degrees C or 68 degree Fahrenheit range. But if you look at these three plots, one is the right side of the plots is essentially the right side of the plot is now, and then it's 800,000 years back on the top panel, 2,000 years back in the middle panel, and since 1880 on the bottom panel. Look at the rise that has happened since industrialization or industrial revolution, and compare it with the ones on top. So two things. The one in the middle panel shows how this is called the hockey stick rise that people talk about. It's almost like a hockey stick. And the other thing is, so that sharp rise is worrisome, and that is where the tipping point might be for everything to drop down. That has happened before. remember one thing, we are in the year of 2020. So our civilization is kind of 2000. If you go back to Mahabharata, Ramayana, it's 5,000 years old. That's it. Before then, the earth has seen civilizations, maybe not like ours, but some, and earth has seen changes in the climate. And look at these falls. They have been drastic. They have not been a gradual fall. Every time there is a fall, it's like 100 years, tens of years. And that's the worrisome, that once the tipping point arises, it will go back to the ice age that we came from and have a habitable situation now, but that might not last. Okay, so why does it happen? Well, we know about the greenhouse gas effect. Essentially, it's the carbon dioxide that we are feeding into the atmosphere, which is a porous gas. After nitrogen, oxygen, argon, it's the carbon dioxide, which is much less than even 1%. But the property of it is so amenable to trap heat in the atmosphere that it just traps the heat that is being radiated out of the black body that we call the geosphere or the Earth's surface. And then it pushes back that heat, and then it warms it up. So the more carbon dioxide we put in, the global temperature average goes up. And that is exactly what is shown in the scaling curve, the greenhouse effect. So essentially, it's the warming because of this shed of carbon dioxide in the atmosphere. A natural effect of that, the warming, is the sea level rise. Could be because of melting of ice caps, could be because of thermal expansion of the seawater, because three-fourths of the ocean is three-fourths of the Earth's surface is ocean. And so there is this steady rise, and the last part is from 1990s. We are seeing with altimeter or satellite measurements. It's pretty well, the tide gauges and the satellite measurements are pretty well showing us the total increase of sea level is about 8 inches per 200 years. That's a lot of inches. That's a lot of, it's close to um, 10 centimeters or so. So, or even more, it's actually 30 centimeters or so. Okay. So there is the sea level rise, there is the temperature rise, and both are caused by things like carbon dioxide. And you can see how the sea level or the Arctic has been melting, which is causing some of the sea level rise in this. So this is a NOAA GFDL climate model simulation in a particular scenario in the IPCC context. And you can see it's 1956, 1970s. That's when the Arctic was full of ice. Slowly and steadily, it is getting rid of that ice. And this is 2020 just passed. And 2050, 2070, 80, 90, and 2100. So already we are seeing an Arctic circumpolar current. We are seeing new ports developed in the Arctic. We are seeing Pacific species coming into Atlantic because now there is a channel around Greenland and around the Arctic, whatever little is left of it. That used to happen only one time in summer. Now it is happening quite a bit of time within a year period. That is alarming. And if you look at the Arctic ice and compare it 79 to 2007, you can see it's the extent of ice is low, as well as the thickness is low. And remember, Arctic ice thickness is much less than the Antarctic ice thickness. And so there is a huge chance that we will actually see 1885 to 1985, it's like halved, and we won't have any ice in 2085. What will happen to all that water? There are simulations that shows parts of Boston, parts of New York will be underwater. And let's see what happens after that. So Arctic is not alone. This is a picture of the Gangotri Glacier. And in 1780, the glacier was here. 1900, it was here. 1971, 2004, I think, is here. That's about 26 kilometers of ice in the glacier is gone now. Okay, so it's happening everywhere. And warming in the Bay of Bengal is also has been tremendous. This is a paper in 2009, I think, and we looked at 25 plus years of data. And you can see near the Sundarbans in different regions, and you can see the warming by almost 2 degrees in 25 years. A recent paper by Seal et al. From IIT Bhubaneswar has shown that the the cyclones generally in the Bay of Bengal are a autumn phenomena. It happens in the fall, in October, November. But there is also some cyclones that happen in May. And an example was there was Fani and Amphan, and there is the shifting seasonality of these April-May cyclones that they tend towards the west, the western boundary. And there is a western boundary current, and that feeds the cyclone, and they're becoming more dangerous. And this was the paper. So warming has an effect, and this paper talks about the warming and how it affects the cyclone's movement and intensity. Okay. Now, just think about when we talk about warming, we talk about a degree centigrade, which is like 2 degrees Fahrenheit. Now, does it really matter? Well, it does. Small change is actually a big deal. And this is from Bill Gates's book in 2021, where he talks about some strategies on mitigating the climate change. So Ice Age was about 6 degrees centigrade lower than now. That's it. Okay, 6. Age of dinosaurs was about 4 degrees centigrade higher than where we are now. It's 4 degrees, just 4 degrees. And crocodiles will be living around Arctic. That's the fear. And if dinosaurs and crocodiles are living on land and ocean, we have no place to go. So things will be very, very different in case this global warming becomes a reality to the extent of about 4 degrees C. So that is why people are panicking to the 3 degrees or 2 degrees, and they want to get it down to 1.5 as soon as possible. And it will take some effort to do that. However, we all want to develop, right? And this is, and we want to develop like the developed countries have developed. So the developing world has really aspiring for building one New York City every month in one corner of the world for next 40 years. That is one model of development of developing world. That will give you 12 times 40, 480 New York cities with 2 million population in each of those cities, which will lead to almost 1 billion people of the 7 plus 2, say, 9 billion people, so 1/10 of the people living in new cities. Just think about it. And if that is not something that you want to think about, just look at this. It's a comparison between two phases of Shanghai. Shanghai 26 years ago, that one, with Shanghai 26 years later now. And imagine the amount of steel, the amount of glass, the amount of cement, the amount of plastic that has been used to make that city of 2+ million. And that is what is going to be happening to probably many cities in India in next 25 to 30 years, many cities in Africa, many cities around the world. And that is what development is, and that is what requires too much of fossil fuel. All that steel, cement, plastic, glass requires fossil fuel. And that's where the emission will be forever and ever. So we have to think carefully. How do we do this? How do we manage this? And all that electricity that will be burned, all those people using cars. So that's the problem of climate change. That is where mitigation has to happen. Adaptation will be okay, but mitigation really has to happen. So again, going back to carbon dioxide and temperature, that's the key. So talking about this temperature rise, how does Earth maintain its thermal equilibrium, if you ask that question? And I think all of us as scientists here, we are legitimately asking this question. And I think the answer is well known now, that that because of the sphericity of the Earth, we get less heat. So this red curve is what the amount of incoming radiation from the sun that you get and absorbed. Then you have the more or less similar black body radiation back, the long wave radiation back into the atmosphere. So there is naturally a surplus in the equatorial region and a deficit, and that is why the poles are cooler on the northern side and the southern side, and then the equatorial region will be warmer or having surplus of that heat that is coming in annually from the sun. Now, that heat needs to be transferred out from the equator to the poles. Who does that? And that's the maintenance of the equilibrium. So like I asked in the previous slide, that what does maintain the Earth's thermal equilibrium? So it is essentially, if you think, and this is the point that I want to make, is that it's the currents in the ocean, and it's the cyclones in the Indian Ocean, the typhoons in the Pacific Ocean, and the hurricanes in the Atlantic Ocean that takes the heat from the equatorial region and distributes them to the poles on a continuous basis. If you think of Earth's this cycle as a heat engine, the Carnot cycle, then the vorticity shading, or the hurricanes, the typhoons, and the cyclones, is essentially the exhaust of that heat engine. The way it works is that during summertime, you bring this heat up, and then during fall or autumn, you have those exhaust working. all of the northern hemisphere cyclones or hurricanes or typhoons are generated in the equatorial belt, then move northward. All of the southern ones, they move southward, right, to the two poles. And very few of them, if ever, rare occasions in which one cyclone or typhoon or hurricane will cross the equatorial belt. Okay, so they're necessary, but imagine what happens in a changed climate. You have excess heat in the equator. You need more cyclones. You need amplified cyclones, or the cyclone's intensity will be higher. So it has to be more frequent. It has to be even more energetic than the ones previously, just to get rid of that heat that we are putting in the atmosphere. That's essentially, my friends, is the problem of climate change. And when we say that, well, warming causes more cyclones and more intensification, that is why it does that. In the ocean, it's little different. It's the currents that matters. And this is a picture of the large scale current system, the mean flow in the ocean, which are actually forced by the wind system on top. And the red ones are the warm currents. And if you look at the arrows, they're actually going from the equatorial region to the poles again. And they're carrying the heat. Gulf Stream is a big carrier of heat. About half of the heat in the world ocean is carried by the Gulf Stream. Another third is carried by the Kuroshio, the others by Somali current and Brazil current and Agulhas current and the Nemo current or the East Australian current here. So there are also these Labrador current and Canary current and other cold currents which are bringing in cooler waters from the polar region to the equator to cool the system. Then there is a deeper thermocline circulation and all that, which we will not get into. The point is that we have to understand these because the Gulf Stream, for example, and as it carries the heat towards Europe, it makes the atmosphere above it warmer because of its own warmth. And that warm air then warms up the Atlantic. And there is a movie, The Day After, if you ever watched it. There is the hypothesis with which the movie starts, and it says that what happens in a warming climate, that if there is no more need for the Gulf Stream to take the heat into these regions, and if these places as warm it is, and there is no ice here, then this Labrador current will not flow, the Gulf Stream will not flow all the way to the European continent, the Gulf Stream will fall back. And if that does happen, then Europe will freeze the first. The ice age will start happening right from Europe. And that it's a paradox in the way it works. The warming will lead to ice age. Okay, and that's the theory. And so the ocean is so important, and in this climatic context, because it reserves the heat, distributes the heat, and it does it so silently that we often ignore it. But there are signs of Gulf Streams flowing down and all that, and that's worrisome. Talking about the Gulf Stream, a little bit of history, and how am I doing with time?
It is fine. Yes, we are enjoying.
Okay, okay. I was not sure. Okay, so a little bit of thank you very much. So And a little bit of history. I'll take you back about 200 plus years, 250 plus years or so. In 1760s, when this was the circulation of the earth that people knew of, it was an old map. The point is, there's the Atlantic Ocean. There is well, those days it was America, a British colony, 1760. So 1776 was when America won its independence from the British. It was under British rule, it was a British colony. And this is the days before Wright brothers. And so letters used to be carried by ships from New York to London and back. And so it goes that people in London complained to people or the postmaster in New York. Actually, let me just share the next one. If you have not recognized him, I put the name there, Benjamin Franklin. He was the first postmaster general in Philadelphia for the American colony of the British in America. And in 1960, Benjamin Franklin, when he took over, and if you ever go to Philadelphia, you will go to the first post office in the US. And he was there and he got these letters from New York and from basically Londoners who complained that when they received their letters from people in New York, Philadelphia, Boston, they get it in 2 weeks. When they write their letters and they send them here, it takes about 3 to 4 weeks. And that was like Benjamin Franklin received at least 500 plus complaints like that, and they were stacked. Those days, mail was carried by ship only and only ship. So he started looking at it and he said, this is a real problem, and why is this so? So Benjamin Franklin had a nephew whose name was Timothy Folger, who was in Nantucket, in fact, very close to where I'm sitting right now, in Nantucket, close to it's an island off of Martha's Vineyard. And Timothy was a ship captain, and Benjamin Franklin was actually a Boston boy. They moved out and settled in Philadelphia. They were having some drinks, and Benjamin Franklin talked to Timothy, and then Tim said, "Uncle Ben, I think I know what might be happening. There is something in the ocean that helps us when we go from New York to London. And when we come back from London to New York, we follow the same route and it really fights with us and our speeds are low. And that's why we come late every time we come from London to New York." Benjamin Franklin said, "Okay," thought about it. He looked at the ship logs for a year and he studied the ship speeds. Benjamin Franklin was not only the kite master and the statesman that he was, but also a great thinker. And look what he did. He said, "Tim, I'm going to come with you for next 1 year in one of your ships. And I'm going to take measurements of the ocean with a bucket and a thermometer." He took the temperature of the ocean across some lines that Timothy showed, that here is what flows towards England, and this is how we go. he did that for about 2 years. And if you go to Philadelphia and go to the library, you will see his work there. And he charted the path of that river in the ocean that we know today as the Gulf Stream. Okay, so the Gulf Stream has a speed of about 2 to 4 knots at times. The ship speed is about 10 knots. Do the calculation. If you're going 10 knots today, it used to be 6 knots maybe at those days. If you do the calculation, it used to be 10 knots when you were in the Gulf Stream. It used to be 2 knots when you're facing the Gulf Stream coming back. It's called the Franklin-Folger chart. It's there. It was actually lost for 200 years when Philip Richardson from Utsol Oceanographic recovered it in 1980. It was there in the Library of Congress in France, and it was first printed in London. It's an amazing story of what Benjamin Franklin did, and the credit goes to him. We actually did numerical model simulation of the Gulf Stream in 1996, and I write this in my book. And we were very happy to even match what Franklin did way back in 1760s or 69. Okay, so that's how Gulf Stream started. All the research that Franklin did, it's different now. Well, but the main path is very much like that. It's a steady stream. It's about 150 kilometers wide, and and 4 kilometers deep. So you can imagine how much of flow. It's about 150 Amazon rivers. Okay, and it carries a lot of heat, and that warms up the temperature. If the climate system warms up, that is one of the things that will have a major impact on the whole Earth. If you now come back to 21st century or even 20th century, there are satellites which are viewing the Earth. And it told us that, yes, Benjamin Franklin was right, but there is more. There are these eddies of the Gulf Stream system. This is a picture from a satellite. Infrared signal gives you the temperature of the skin of the ocean. And that's how we know which regions are productive, which are not, and all that good stuff. And you can see the warmth there. And this first CSAT was 6 months of lifetime, but it told us that there are these eddies galore in the ocean. And that was in 1978. India's first ocean sat was in 1990s. I don't remember exactly, 92 or 93 probably. There was an experimental ocean sat somewhere in the 80s. So it's an amazing treat to look at the ocean from satellites. However, you need the instruments to go down because satellites can only see the skin, and it's 3-4 kilometers deep. So you need instruments that go, and there are new instruments now which are surveying, and there's a lot of fluid dynamics. There is a lot of interesting processes that happens. It's a fully nonlinear coupled system. And then if you couple biology with it, chemistry with it, geology with it, it becomes a fantastic paradise for any scientist to dive in and work. Okay. Just to give you an idea of what we do with those satellites, this is a picture of two typhoons in the Indian Ocean, one here and one here, but you can see that they rotate in opposite direction. This is a very rare figure that, or rare image that was captured by one satellite, and in one spot on December 30th, 2011, two cyclones captured in one shot. It's amazing. Okay, to give you an Indian context of things, there are a lot of stuff that goes on and monsoon is as old as the civilization. And the Indian context is very rich with monsoon. And we do have interesting things in the Arabian Sea. There is oxygen minimum zone. In the Bay of Bengal, there is a huge salinity contrast right where you are sitting there because of the Ganges, Brahmaputra, Meghna system. And then the equatorial influence is too much. There is El Nino-like phenomena in the Indian Ocean too. Sometime back in the time when Benjamin Franklin was doing all his work on Gulf Stream, there was this person, James Reynolds, was the first Surveyor General of Bengal. He came to India in one of the as a shipmate in one of the East India Company ship, and with his young wife at the age of 21. And then he started surveying the whole of India. And then there is this other person, Gilbert Walker. And I don't know if you know of him, but he's an amazing person sitting in the Geological Survey building in Calcutta or Kolkata now. He was mapping the world's pressure systems, because at that time Britain used to own many of the colonies all over the world, and they had some Royal Meteorological Society in various places, and he wrote to them, got their pressure data, and discovered two very important things in the climate system. One is called the Southern Oscillation, which we know is related to El Nino in the Pacific, and the other is the North Atlantic Oscillation, which is in the Atlantic. And that was Walker's contribution to sitting in, and if you go back to IMD reports, you will see them in the 1912s and 1902s, his papers right there. However, I did not know for a long time. I knew of his work, but recently I came to know that the Ewell-Walker equation that people do, if any one of you are doing spectral analysis and autoregressive methods and all that time series stuff, the Ewell-Walker equation, that Walker is none other than Gilbert Walker. So it's amazing how that meteorologist has spanned into different areas of science. And this is the map of Hindustan at the point where James Reynolds, he's called the father of oceanography. In fact, in England right now, it's the Reynolds Institute of Oceanography. And that is the map of Hindustan that he created, and the Bengal Atlas in 1776. And if you look at the Sundarbans there, it's amazing how clean it was in those days. And probably someone needs to compare what this is with the GIS systems that we have today. Okay, bringing you back to where you are, cyclones have been very prominent thing in people's life, especially in Northeast India. And out of 410 cyclones that we know from 1877, that's about 200 years to 2000. This is the distribution district-wise in Orissa. And amazing that 1 out of every 4 cyclones has passed through the state. And you are, I believe, somewhere here, sitting there. And this is why we thought of doing something. I'll come to that. But if you if you look at what happened to, and cyclones are coming, and every year they're a problem. But let me tell you this story about Phony. The cyclone Phony was in May of 2019, I believe, and that was the path. and you can see how.
Yes.
Sorry.
Professor Chari wants to say something. Professor Chari, you are mute.
Professor Chari, you want to say something? Okay.
Two slides back. 2 slides back.
Okay.
What is that number that you have put in one more? Yeah, that 172013. What is that number?
That should have been 17, 20, 13,
sorry.
7, 8.
No.
I'm sorry about that. My student prepared it. Yeah, it's if you add them, probably will lead somewhere to that 101 or you're probably somewhere.
Okay. Thank you so much. Okay.
Yeah. It's a district wise that helps the GIS people.
Okay, thank you.
So talking about funny, and it's an interesting story, and I think this comes back to what I started with, Sir C.V. Raman's quote that you start studying a natural phenomena and then you realize how that can become a branch of new science, and cyclone is such a thing. So you have seen the devastation, and you can see the rage of the cyclone through the Indian coast. Now, Funny was there, and it was in 2019. If I take you back about, say, 30 years, 20 years, 1999, if you remember the super cyclone, that took about 10,000 people's lives. Funny took about 15, maybe 20, I don't know, somewhere around there. We could not save them. I mean, you'd love to have a number 0. But let me take you back 50 years. There was a cyclone called Vola cyclone, which took the toll of 500,000 or 5 lakhs people were dead. It went through Sundarbans, Bangladesh, part of Odisha, West Bengal, Bangladesh. And Vola cyclone is probably the second largest calamity in the cyclone's history in the world, something like that. Super cyclone in 1999, 10,000. Compare the numbers. Funny in 2019, only 14, 15. How did that happen? Well, if you think, in 1970, we did not have the capability to predict the cyclone. We did not know when it is coming. We did not know where it is coming. It just came and took us by surprise. In 1999, we had the predictive capability. We knew that the cyclone is coming, but we did not know how to take that information to people. We did not have the cell phone capability that we have today. We did not have the smartphones. We did not have the messaging capability to tell 5,000 fishermen who were lost in those seas of that 10,000 lives lost. There were 5,000 of them were fishermen. In Fanning, 2019, there were a 3-4 days warning. Every fisherman knew 4 days ahead to come back to shore, take shelter. There were shelters in place, and information, technology, predictive capability, all that is giving us the thing that we wanted. So from 1970 to 2019, 750 years, we have progressed a lot thanks to the science, thanks to the technology, and thanks to the communication ability of us, right? And IISER has done a great job. In fact, IIT Bhubaneswar has done a great job of predicting funny, and IMD and all those places creating shelters, all that was there. The whole government machinery works. So that is the success of science, I would say. And it all started with understanding cyclones and understanding their predictive capabilities that led us to this. Two important science contributions that I think noteworthy. One is observation. You have now observation capabilities in the ocean. That prediction does not come easy. It comes with real-time observation. Just like after tsunami, we realized that we have to observe the ocean in real time. There are instruments in the ocean, satellites, like I showed you, in real time. Internet data distribution in real time. That data has to come from the ocean to your desktop so that you can run your models, which are very high resolution, and they're resolving multiple subgrid scale processes, starting from mesoscale to sub-mesoscale and then to finer scale phenomena. You need to assimilate those data in your models to adjust your models and produce forecasts every 6 hours or 4 hours as you get more data and more data. That is why the cyclone paths keep changing, because you're adding more data to the models. But the cone of influence is a key to get people out of the danger zones. That's how it happens. Okay, so I'm going to move through quickly now, I think. Essentially, if you want to understand climate, land, earth, atmosphere, oceans, rivers, biosphere, I could not think of anything more, but maybe there are some more. Estuaries is one. It requires multiple disciplines to work together. It requires multiple modeling framework. It requires all kinds of observations over multiple scales, over multiple disciplines to put together. And this is what needs to happen. There are now instruments in situ as well as satellite, which are giving you real-time data. And this is just an example of what the global network of ocean network is. And add to that the atmospheric network, you will have your climate system. There are models which are very complicated, and this is just an example, and they all talk to each other. Neural networks is a great example of models that that people are using now. Different kinds of disciplinary models: physics, chemistry, optics, acoustics, biogeochemistry, and all that good model stuff goes into predicting something like a cyclone. Now, why am I talking about that? And what's it's an eye-opener when I started looking at this after spending so many years in US and going back and forth between India, Brazil, and US, realized that population-wise, we are way up there, whereas there's only 3 or 4 institutes now that is dedicated to ocean, climate, and environmental research. Whereas US, you have 20, Japan, you have 5, 15, and look at their population. Okay, so there has to be something brainstormed through and talk about this. A new initiative has begun. This is a marine campus very next to your campus, and hopefully it will start soon. There is that piece of land there. The elements could be many, listed here: infrastructure, and I'll show you some of these. The problems are too many. We know that there are processes, the cyclones, the rivers create problems, and I can go through all these details, but right now I'll just leave you with this schematic. It's a complicated system, but it's a system that can engulf all the atmosphere, the ocean, the land, the melting of the ice, the monsoon, and everything else uh, into it. Science questions have been identified, and I don't want to get into those details right now. There are low-cost observational techniques that we can easily start things from a small research vessel, and that's where we should probably start. And that's the plan. I think Professor Chari and Director Raja Kumar and MOE secretary we were discussing, and hopefully this will happen soon. There are enormous research possibilities. The whole world is waiting for something to happen in the Bay of Bengal area, and Indians should do what it takes to be done. And there are phases of research and observation that has been planned, and it's a matter of time that should happen in the next 10 to 15 years, I would hope. Okay, so that brings me to the final message. What is it? Okay. So to the young people in the audience, when you look at a problem, you always look for a solution. I would say that look at a problem, invert it, and look at it as an opportunity. Then you will find a solution. If there is a problem, that means there is an opportunity to solve the problem. If you take that step first, it'll be better. And I have used this approach, and I always find that an opportunity is a much better than trying to think of solutions, because now you can think of multiple solutions. You just don't have to think of the solution. Let us recognize two things first, and this is important, I think, for at least for me, who is above 50 now. There is a new generation of learners. The students that are coming into, at least in UMass that I have seen, the entering batch of 2022 was born in 2005, 2006. The first iPhone was released in June of 2007, where these folks were like 1 or 2 years toddlers, right? So they all grew up with phones in their hand, okay? And the teachers that are there now, who is less than 40 years of age, they have never used a slide rule. I forgot when I used a slide rule or an adding machine. I did that. And they all have worked with a computer, at least from high school, I think even from middle school age, and they're very internet friendly. So the teachers can become the enabler of knowledge at a very fast pace that I have never thought of doing. And this is a real opportunity for us to move ahead with science. Because I think, like my mentor at Harvard told me once that, and he used to tell it often actually, the 19th century was the century of science. And that scientific development brought technology to the forefront, okay? It brought us the computer. The 20th century was the century of technology, right? And then in the 21st century, technology is driving science now. We are seeing things due to the technological advances that we have never seen before. We are seeing scales that we have never seen before, and we can hypothesize more. We can come up with new theory, and we can come up with new science, new understanding. We can connect disciplines together. we can connect the society into the framework, and you are seeing that happening with big data, with other important initiatives that are being done where science is becoming mingled with everyday life. Technology is driving science, and if we recognize that power and create opportunities, I think that's the way to go to essentially save the world. Or if I could take a quote from Mahatma Gandhi, who said, "The earth, the air, the land, the water are not an inheritance from our forefathers, but it is actually a loan from our children. So what we have to do is we have to hand it over to them as we got it from our forefathers." I think that is a statement of sustainability of the earth, sustainability of the environment, sustainability of the climate. And Mahatma Gandhi said that very well, that it is not us to just use it and then go from here. It is for us to preserve it for the generations to come. And with that, I would be happy to take on any questions. And I'm sorry that I got so late, I think. Thank you.
Professor Avijit Da, before anybody asks a question, I want to seek your permission to use some of your quotes in our campus.
Oh my goodness. Please.
In permanent campus, I want to use this last as a quote somewhere else, or some quote some places that and want to wherever appropriate. So seek your permission. So
Please
thank you
feel
very much.
free.
Sorry to
Feel
intrude
free.
before anybody could ask the question. Thank you very much. Yeah.
Yeah.
Please feel free.
Let me
Yes,
just
Professor.
put one question to you, Professor.
Sure.
You have shown those 100 odd cyclones which were hitting Orissa, different districts. Could anybody classify the trajectories of these cyclones with having a particular path, a more favored path than unfavored paths?
It's a very, very interesting question, and I would like to share with you. Maybe if I go back to, so I was showing you, so you've seen that path, but let me share this particular figure.
I think you crossed that.
This one.
Uh-huh.
So if I'll send you this paper to share. This is just a paper from 2021. And you can see so these are most of the cyclone paths in, so this is 1982 to 2000, and the paths were like this. Okay. And you can see the favorable paths. I mean, these are the paths. And that's because of the ocean temperature and where they pick the energy from. Okay, as they're generally generated in this region, the depressions, and then depending upon the favorable conditions, they become the cyclones. Now, recently what has happened is because of warming, the generation region has shifted to southwest. And this is where both Funny and Amphan were generated. And then they follow the western region. This is Funny, this is Amphan. And you can see them that they are going over this western boundary current region. This is a mini Gulf Stream in the Bay of Bengal. And that happens in the springtime, April, May time, because of the seasonality of the winds. The winds change, and the winds actually forces the circulation in the bay or any other ocean. So yes, there are these preferred path, but what you are bringing up is, has anybody done a clear analysis of why? I don't think that is yet known. That's still an open question, and I think it will be very interesting to take a look at, because we do not have, other than the satellite data for last 30 years, we do not have much data in the in the layers below. And it is the heat content in the upper mixed layer, so about 100 meters, 200 meters down. So you have to get that heat content. That's where the energy of the cyclones come from. And so I would say Professor Mohanty might be one person who has done lots of reanalysis, and and talk to him about this. He might be able to guide us to a particular paper or a series of paper. Maybe NCMWRF and IMD, they might have something on that. But there is the preferred path, like we are seeing right here, is that. Why that? Why not this? Is a very good question.
Thank you, Professor. I leave it to the others. To Professor Sridhar, you have a question?
I don't have a question, but I do have a very short comment. For a person whose ignorance was absolute, to be enlightened within an hour, I have rarely sat through a better presentation. I immensely enjoyed your presentation, the historical angle, Benjamin Franklin's work, and then bringing it all the way to what IISER Berhampur can do. Brilliant, absolutely brilliant. Thank you, sir.
Thank you, thank you. I hope that that translates into reality.
Yes, yes, yes.
Professor Chari is listening, I think.
Yeah. Yeah. Please, anybody from the students and the faculty?
Can I?
I saw someone raised a hand some time back. Sorry, go ahead.
Please. Can you unmute yourself and then?
I have unmuted. Can you hear me?
Your volume is very low.
Yeah, barely.
Hear me now?
Better.
So, good morning to all of you. Good morning. Good morning, Director Sir. Been associated with the.
I think your voice is very feeble. What you can do is that you can write
On the chat.
on the chat box.
Anyone else while he's writing?
May I ask one question?
Anybody else?
May I
Yeah,
ask?
sure. Yeah.
It is audible?
Yes, you are.
Yeah, thank you. So I'm Prosenjit, the faculty of chemistry department. Thank you very much for this nice talk. I just continue to our director sir's questions. Like just in my childhood, during that time, we know that there is lot of floods and all those things, and by that time now we can able to control the flood, like river flood and all those things. But maybe in the near future, do we able to control the cyclone, like wind speed, or how it is generated? Like if we have a lot of knowledge, like how it is generated and how it can create on that science background, then we can able to control that.
That's a very interesting question, and let me answer it in in two parts. And I have I have two thoughts on that, but I think the straight answer to your question is that yes, it is possible, and I don't know if you have heard, but if this 1st of January this year, there was rain in Dubai, on the city
Yes.
of Dubai,
Yes.
and that was artificial rain,
Yeah.
right?
Yes.
And that was artificial rain on the city of Dubai, created by scientists who created the clouds,
Cloud.
and
Yeah.
then they did
Artificial
not
cloud.
know. Yeah, artificial cloud, and then they did not know where it was going, and eventually the wind takes it to the city of Dubai, and then it's falling there, right?
Yes.
And then they so that's doable. Cyclones intensity, they have there are these hurricane hunters, US military aircrafts, and they go down, and there have been experiments to try to kind of burst out the big convective cells before on the ocean before they come on land. And that is on the experimental stage, I would say. And so that is being done. That is being done. But how far away we are in realizing destroying real hurricanes in the ocean, I would say maybe 40, 50 years. I'm glad I won't be there that long, but so you can't hold me to it. But the so that's the answer to your question, and I think it's in the process. It will happen. The other question I would ask to your question is that something we really want to do? Create nature and in nature's or come in nature's way? I don't know. It's more of a philosophical question, but I would
Yeah.
leave that to you to think about.
Yeah. At
I'm
least
not in
we can
favor of
like
it. I'm
what.
not in against of it. It's just a question that comes to my mind, and I think there's some pros and then some cons, and it's like the development.
Yes.
It's very much like the development, and on one hand, I want to see people live comfortably, but at the same time, I don't want to follow the same development path that others have followed. But I do not have a good answer for my path that I want because I do not know.
Yeah. Maybe like we don't want to destroy them, but maybe in the control them, like that may be good for human.
Yeah, maybe. Yeah.
Okay. Yeah. Thank you
So
very much.
that's a good thought. Yeah, maybe bring them down to category 2 or category 3. But that's like more on the path of adaptation rather than mitigation of climate change. Like I said, that we are warming the planet, and there will be more and more of these natural disasters happening, and more frequent and more energetic because we have more energy in the system. So they need to be redistributed.
Yeah,
So
means
how
from
do we do
chemistry
that?
point of view, we are working on this like global warming, like circulation
Mhm.
economy and carbon dioxide reduction, but still it is under like in the laboratory scale, not in the general scale.
That's fine. That's fine. I mean, it might take your lifetime to do that, but you will come up with something eventually because
Yes.
it's a long battle, and we have to all fight it.
Yeah, means renewable energy and all those things is going
Yeah.
on, but
Right.
maybe in
There are now the
yeah.
Sorry.
There are few more questions.
Yeah, sure. Thank you very much, sir.
Yeah, this is from one of our faculty from biological sciences, Bodhisatta. He is
Okay.
asking you, if this is the age of science, unfortunately, science effect on society is also dependent on people's mentality. For example, advances in quantum physics can be put use in both destructive and constructive ways. depends on what the society's mindset is. Sad to see that when the world is facing global crises such as climate change, hunger, pandemic, etc., half the world is in a war or on the verge of a war. How can a young mind feel optimistic about the global state of affairs? What are your thoughts?
Did you have to ask that question? Yeah, I'm in two minds. I mean, till 9 o'clock my time, I was watching the news, and I completely agree that it's, as a scientist, and I have gone through this myself. I go through this every day. And then I think about Einstein at the end and what he said. I mean, if he knew that this would happen, he would have never done it. Right? But we don't know. When we discover something, when we invent something, we do it for the fun of it. Then someone uses it for a different purpose. That's the problem of human society, because I mean, I will be amiss, and sometimes I give myself comfort in the words of Ramakrishna, that when he said, a candle gives the light. Someone reads in that light, someone takes the candle and steals someone else's stuff. It's not the candle's fault. So I don't know how to answer your question. I cannot control the minds of so many human beings who are, in my view, in a different path. All the development that we have done could be destroyed in one night's bombing, right? I mean, that's what we are seeing. Beautiful city can be destroyed in one night because someone thought so. And no one can stop him.
Mm-hmm.
So that is there. The only way that we can, and I think, and this is a problem of the way we grow up, the way we teach ourselves, the way we teach our kids are very different. And the value system has been torqued and torn apart by people to work on their own benefit, and that's a problem. I'm just stating my view, but I do not have a solution for this. On the other hand, I think I blame some of the world leaders who had the opportunity to do things at a point where they did not do it. And like, I was totally opposed to going into Afghanistan or into Iraq way back when. And but I mean, right now, what we are seeing and what we are experiencing is something that I would hope is temporary, and the good will prevail over the bad thoughts. And that's the way I always looked at it, and I think I have benefited from it. I know it's hard, and it's difficult when you are a young investigator and you don't know where to set your mind and why even you are doing this. But I would say science at the end always wins, and it has won, it will win. And that's the belief and If you believe in that, go for it and leave
Thank you,
the
Professor.
other things. We are scientists, we are not politicians, and we can inform them. What they do with that is really, people have given them the power, unfortunately, and that's what is going to be. That's the way the world is, and we just hope that someday John Lennon will be right and it'll be a better place.
Thank you. There's another question from Vivek Tiwari, faculty from Biological Sciences. What is the impact of cyclones on flora and fauna density in the long run? Does it eliminate or bring new ones as a source of evolution?
That's a very good question. And there have been a lot of studies with impact of cyclone on the flora and fauna and in different oceans, especially in Atlantic, in Australia coral reefs, and other places. And the cyclones actually do take what, maybe 3-4 days to pass by that whole region. So you're seeing, looking at that plot, you see that it's like a week or maximum a week. Yeah. So, and it crosses the Bay of Bengal, right? So there is a restoration time. So, and there have been studies there that it does not um, destroy the system completely, but it takes, the mangroves get destroyed quite a bit, but then they grow, and there are restoration time periods, and there are restratification time periods in the ocean, but those are on the order of days again. So things energize up back to their, it's not a real hysteresis curve, it's more like gradual coming back to life, if that helps. And I can, if you send me an email, I can send you some papers, and a lot of work is being done with interdisciplinary modeling. So you need a physics model, you need a chemistry model, you need a biological model, and then look at the biological impact of the physical setting of the cyclone. Yep.
Okay.
But those are continuously being studied, and in Bay of Bengal, those studies are rare. So that is something that we should be thinking about doing. How does the ocean environment and flora and fauna changes with cyclones? Very good question.
There's yet another question from Dharmarao, the visiting faculty in the upcoming Earth and Environmental Sciences. His question is about PETM. You must be knowing about that abbreviation, where carbon emissions have been at the peak with an average global temperature of about 8 degrees centigrade. If Earth has maintained its thermal equilibrium 56 million years ago, why not now? Are we making too much on anthropogenic effects, ignoring natural increase in temperatures due to sun's rotation tilt on increasing temperature?
I will defer that question to someone more knowledgeable with all the geology and geological past. But the only thing I can say is that, I mean, he might know better. The anthropogenic, I mean, there are models that definitely says that the anthropogenic input right now that we are putting is extraordinary and has caused the temperature change. So it is anomalous, and that anomalous temperature rise has happened due to anthropogenic CO2 input. So on one hand, I think we are adding to the natural cycle, And if we know that, then should we not do something about it? That's my point. And because we only have, we are starting to, the earth might be there. It's not that earth will not be there. Will we be there is the question. The
Thank you.
humans. That is the question.
Thank you so much, Professor. I think it has been a wonderful morning for us and wonderful evening at your end too, I suppose. And on behalf of entire fraternity of IISER Berhampur, I thank once again. And as a token of love, we present you a nice shawl virtually. Okay. And as you
Okay.
shared that when you are here in 2 months, I think you will have it with you. For the moment, I mean, just accept this virtually. This is a specially made silk shawl. Okay. As a matter of fact, Berhampur is known to be a silk city. Okay. So the IISER Berhampur has come up with this model, especially for people like you. Okay. Please accept this virtually. And if you want, I can send it by post. Otherwise, if you're coming in 2 months, I think you can have it in person too.
I would say keep it with you. I'll come to your campus and accept it.
Thank you so much. You must visit, and you should, as our Professor Yogendra Sharmaji was also saying, that we would like to have you with us. And maybe if it's possible, rather you can give a course to our young minds and then be part of it, our evolution.
Sure, would be happy to. Would be happy to.
Thank you so much.
It's been an enormous pleasure talking to you all, and the questions that you are asking tells me that you're so interested in this subject, and I'd be happy to discuss further with you, Professor Chari, and everyone else. It's been a pleasure. Thank you very much for the gift. Please keep it. I will be there in summer, sometime in, I think, June. So would be happy to meet with you.
Yeah.
Yep.
We will try to plan something for that time.
Sure.
Thank you
Good
once
night.
again, and bye. Namaskar.
Good night.
Good night. Bye.
Bye, everyone.